We're going to get a little more in-depth into our probability. This really isn't overly complicated. We use some funky terms, but once we start thinking about it, it's not too bad. So we're going to start off with a couple definitions here. The first one is a random variable, which is a variable with a value that is the numerical outcome of a random event. Okay, for example, it's just a variable. A lot of times what you'll see in the book is that they're going to use x. Okay, so they might say the probability of x. So it's just some event, right, the outcomes of that event. And a discrete random variable is when there's actually a finite number of possibilities. We know what it's going to be. So I have an example here. So let's pretend I was using this situation. Instead of x, I could call this g for games. So I could say the random variable is g for games, right? And I could say that the g is it's got to be either what? 1, 2, 3, 4, or 5 for the number of games played. So that's the finite number of possibilities. We're not playing any more games than that, and I can find the probability of each of those in this current situation. And that's what we're going to do. And we're going to take a look at how it's distributed, some meanings behind it, and things like that. So let's just look at a basic example here. It says the owner of a pet store asks customers how many pets they own. The results of this survey are shown in the table. Okay, so 3 customers all have 0 pets, 37 customers 1 pet, so on and so forth. Let's just do a few questions from there. So this is find the probability that a randomly chosen customer has 2 pets. Okay, we just got to think a little bit, not overly hard here. Well, how many customers have 2 pets? 33. And for probability, how do we find probability, right? It's favorable over the possible. So 33 over, well, I better add all these up. So 3 plus 37 plus 33 plus 18 plus 9, which gives us 100. So that was kind of convenient. So 33 out of 100. Or I could say it as a percentage, which is about 30. Well, exactly. It's 33% as well. Okay. So didn't have to think terribly hard there, but just take a look at the question. What are they asking for? And see how you find that. Same thing for this. Find the probability that a randomly chosen customer has at least 3 pets. So read that carefully. At least 3 pets. Well, let's take a look at my data up here. At least 3 pets. So these have 3. So that at least. And they have 4. So at least means more than that as well. So 18 and 9 give us a total of 27 out of a total of 100 customers. So 27 out of 100 now, which would be 27%. And it's not always going to be out of 100. In this situation, it just kind of worked out that way, which was kind of nice. The other thing that we're going to be doing is we're going to take a look at the probability distribution. Well, we just said that we could use x for an event. So the probability of x has to fall between 0 and 1. And hopefully, I think you've talked about this maybe a year or 2 ago. Remember, probability, 0 means this is not going to happen. And if the probability is 1, that means it's for sure going to happen. And somewhere in between is some decimal that we can make into a percent, right? Right in the middle would be 0.5, which is 50%. So x, we're using x for the event. The probability of x has to fall in between 0 and 1. And the nice part about this is the sum of all the probabilities, if I'm looking at just one event, has to add up to 1. And we're going to look at that in just 1 second. Okay? I don't want to confuse you here, but we'll talk about that in a second. And we have a probability graph, which is a bar graph that just displays our probability distribution. Okay? And we say it's distributed through, since the probability out of 100%, it kind of shows how that 100% gets distributed. And we'll see that here in a second. So let's just do an example so you can really see what I'm talking about. It says the table shows the probability distribution of students in each grade at Sunnybrook High School. We're using X for our event, and the event is what grade they're in. And it has the probability over here, 0.29, 0.26, 0.25, 0.2. I might write these as percents as well. So 29%, 26%, 25%, and 20%. Right? I would just move your decimal 2 to the right. The first thing we're going to do, and the book will ask you for this, but we want to see if this is a valid distribution. And to do that, we have to add up our probabilities and make sure that they add up to 1. Right? They can't be more than 1. They could be less than 1, but then it's not valid. They should add up to 1, right? Because obviously there's only 4 grades in our high school here, so you shouldn't be in any other grade. And if I add up all these, I end up with, it looks good, I end up with 1.00. So we add 100%. So this is valid, right? This guy is valid. That's good. Okay, and then I could find some different things, like if I said, what's the probability? Let's say we're going to pick a student at random. We're picking a student at random. And I wanted to know what's the probability that they're going to be in grade 11 or 12. Well, I could just add up my decimals here. So I could go 0.25 plus 0.2 for a total of 0.45. So they'd have a 0.45 probability, or I could say a 45% chance. Either way. Okay, I could make inferences like that on the data. What's the probability? And I could also make this into a probability graph, which I just showed that definition on the other slide there. So let's go ahead and do that. So I'm going to make a probability graph. So make an L graph here with our bars. Well, the y-axis is always the probability. So the probability of the event, which we called x. So probability of x. And remember, it can never be more than 1. And if you look at it, none of my probability even gets to 0.3. Right? Everything's 0.3 or 0.29 and below. So when I make my y-axis, I'll never have to go above 1, but I'm going to have to decide, do I want to count by tenths? Do I want to count by 2/10? Do I want to count by 500ths? In this case, I'll just go by tenths, but I'm going to space out my, my scale here. So I'll say this is 0.1, 0.2, 0.3. Okay, and then down on the x-axis, that's our actual event, our event x, which in this case is the grade level. And we have what? Grade 9, 10, 11, and 12. And then we just make our bar. Well, grade 9 up to 0.29, which is about up here. So bring it down and we fill it in. Grades 10 is at 0.26, so it's a little more than halfway between 0.2 and 0.3. Somewhere about there. Doesn't have to be beautiful. Grade 11, 0.25, so just below grade 10. Just barely below grade 10. And grade 12.2, so they're a little bit more lower. And filled in. So there's my probability distribution. So we can look, hey, the probability that they're in one of the grades, if I picked a random student, it'd be pretty equal, right? They're pretty close to each other. And that's why we use the graph, because then I can just look at it rather than having to look at the data. Sometimes the data gets to be a lot, so I like to put it in graphs. So this is very basic what we're doing with the probability distribution. And that's really all there is to this. Okay?